Okay, we are back. So problem 3, let's go ahead and go over problem 3. So the first thing is, can you conclude a relationship between the class of vertebrae and whether it's endangered or threatened? So step 1, you could just write down this generically, right? Or if you want to be fancy about it, that's totally fine. And then you'd say something along the lines of H0 would be vertebrae class independent of endangerment, and then H1 would be class dependent on endangerment. So it'd be something along those lines.
Which problem was this?
Lab problem 3? Is this not lab problem 3? On the quiz? Yeah, it is. It's the mammal thing. It's this one right here, the one you guys are just working on right now. When I sent you off, I said work on this problem.
The example 3 on the quiz is the one about
Not quiz. You were not supposed to do the one in the quiz. The quiz we're not doing. We did that last class. We already did that problem. So this is the problem you're supposed to be doing now. It's on the worksheet. That's the wrong problem. That's chi-squared list. That's not even a matrix. And it's also the answers to that were from last class. You should be able to look on your papers for last class, and you should be able to check and see if you got it right from there. Okay, so at any rate, let's go on to this one. So here's this one. Our step 1 is obviously this part here, right? Step 2, our critical values. So we had 2 rows and we had 5 columns. So 2 minus 1 times 5 minus 1, 1 times 4 is 4. Alpha is 0.05, so alpha is 0.05. It's so easy to want to pick the last one, right? Because it says 005, but it's not that one. That's 0.005, and you want 0.05. So you don't want this one. You want this one right here. And 4, so it's going to be this 9.488 right there. That's my critical value. So I'm going to draw a picture. Here's my picture, steep up and then off. And it's going to be, again, shading over here. And that's going to be 9.488. Okay, so then we have step 3. We're going to find our first and last expected values. So, so for the first one, I need to grab his row total and his column total and divide by his grand total, and I'll get 54.2. For the next one, the last guy, he's the last guy, I'm going to take his row total and his column total and divide by the grand total, and I'm going to get 45.3. All right, and then we're going to put into matrix A and use stat test chi-square test of A, and you should get 45.314. So I'm going to go back and pop that into my picture, and that's going to be way out here, right? 45.3. It's going to be way out there. .3 something. I think it's 14. So super far out there, we're totally going to reject H0. So we are going to reject H0. which means we do have enough evidence. And you can either say to reject the claim that proportions are the same, which is kind of the generic statement, or you could say enough evidence to, let's see, my claim was that there's a relationship, so that was H1 to support claim of relationship between class and endangerment. I'll draw that this way. Wow. Okay, endangerment. Okay. Right. So you could just say that instead if you wanted to, and that would be okay. So those are sort of your options. You can either do the basic one, right, the generic one, or you can do the kind of the proper one. On your homework, you're going to need to do the proper one. All right, so let's get on to the second question, which is the result different if we have a 0.011 level of significance? So if we use that, then we're going to be using, again, we're going to be using this guy right here. Don't get it confused with 0.001, that gets confusing, or 0.010. Again, it's going to be degrees of freedom 4, so 13.227. I'm going to shade this way. So it won't make any difference at all, because here is our 13.277, and our value was way out here, 45 something. So either way, we're still going to, there's our test stat, 45.3 or something like that. So either way, we're still going to reject H naught, and it's not going to have any difference on any result on our difference. So remember, when we change alpha, the only thing we change when we change alpha, you guys pay attention to this part. When we change alpha, the only thing we change is our critical value. So it changes where we fall, and then we can kind of see if it's still unusual or not. Right? And here in this case, it is still unusual. All right, so let's hop into chapter 11.3, analysis of variance. So this is the next page of our notes, 11.3, one-way ANOVA. So we're going to test that means are the same. mu1 equals mu2 equals mu3, however many means you have. That's our H naught. We're going to just use the very basics. We're going to use our TI 8384 to compute the results, because it's really complicated otherwise, and that's going to give us our p-value. Once we get the p-value, then we're going to remember what a p-value is. A p-value is the probability of getting a sample like yours. So what's our guideline for unusual, generally speaking, 5% or less? So something is unusual if its probability is 5% or less. So if our p-value, if our probability of our sample is 5% or less, we're going to say it's unusual, and we're going to reject the null hypothesis. So here, our p-value, we're going to compare it to alpha, right? Because it's usually 5%, it could be something else. Alpha is our level of unusualness. So if p-value is equal to or less than alpha, we're going to reject the null hypothesis. If p-value is greater than alpha, then we're going to fail to reject the null hypothesis. So remember, this one we're comparing p-values. Why? Because I didn't want to give you yet another table just for one small section. So we're going to be using the p-value for this one. All right. So this is important. This is kind of explaining some ideas behind it. If there's no difference in the means, I have 3 different means. If there's no difference between them, then the between group variance will be about the same as the within group variance. So we won't reject the null hypothesis. However, when the means are different from each other, very, very extremely different from each other, then the between group variance is going to be a lot higher than the within group variance. I will reject the null hypothesis. And let me explain to you what I'm talking about with that. So let me get up and show you guys. So here's the idea. Say I have a bunch of children, or kids. So some are kindergartners. So they're going to all be about this height. They're going to range from here to here. The variance is going to be about that much, right? They're going to vary from there to there. So they have kind of a smallish variance. And I have fourth graders, and they're going to be about this tall. And they're going to vary from here to here. So this is their variance. Then I have high schoolers, like high school seniors, and they're way up here, and they're going to vary this much up here. So their within group variance is only going to be maybe like that much, right, within their group. Not that big. But if I look at the between group variance, so between the kindergartners and the fourth graders and the seniors, their between variance is like this, right? Between all of them, it's going to be this giant variance. So the between group variance is going to be really big compared to their within group variance, right? Those are a lot smaller. So that ratio of within group variance, between group variance over within group variance is what we're talking about. So, within the groups, they have this kind of smallish sort of variance, right? Their means and their variance. Their variances are all, 5 to 7, not super huge. But when you start comparing them from the little guys to the big guys, then all of a sudden their variances become a lot larger, huge. And so this is what we're talking about. The between group variance or the between sample variance. That's the really big one between the the little guys and the big guys. And then the variance, the within group variance or the within sample variance. So that's just within all the kindergartners by themselves, or within the fourth graders, or within the high school seniors. That's not as big. So that ratio, when you divide them, that gives you your F value. So on the exam, on the final, you're going to be given a between group variance or between sample variance, and a within sample variance or within group variance. I might call it either one of those, or I might call it variance between. I might call it any one of those things, right? Variance within samples, within sample variance, within group variance, variance within groups. Those are all the same thing. And I'll also give you other things just to distract you, and I'll ask you to find F. And if you're sharp and you're paying attention to this, then you're going to say, oh, it's just these two divided by each other, done. Super simple, easiest 2 points in the entire final. If not, if you forget this formula here, then you're going to be scratching your head and trying to find some creative, crazy way of finding F, and which is going to be completely wrong. Right? So it's just this. That's it. Between group variance or between sample variance over within group or within sample variance. All right. Just as a reminder, these are the steps for ANOVA. You're going to first, state the hypotheses. H naught is always going to be mu1 equals mu2 equals mu3 equals mu4, as many mu's as you have. And then H1 is always going to be at least one mean differs. That's it. At least one mean is differs. Then find alpha. Write it down. Alpha equals 0.05 or alpha equals 0.01, whatever it is. Just write it down. Super easy, step 2. Step 3, compute the p-value. Put one group into L1, next into L2, the next one into L3, however many groups you have, and then do stat test ANOVA of L1, L2, L3, L4, however many groups you have. And then it's going to give you a p-value. You're going to reject H0 if the p-value is less than or equal to alpha, and either you will or will not have enough evidence to reject the claim the means are the same. That's it. Super, super straightforward. All right, so did you guys finish? Did you guys, let me know if you guys finished quiz 2 yet or not, if you need more time on that. So please text me and tell me. I don't have any sort of, what's going on with this? It's not coming up. All right, so I'm going to assume that you guys are good. I'm going to go ahead and go on. So here's quiz problem 1, the first one. So first we're going to state the hypotheses, identify the claim. mu1 equals mu2 equals mu3. That's my claim because we're saying that the farms are the same. The mean is the same. So that means it's going to be H0 is my claim. H1 is at least one mean differs. You can't say which mean differs. So it's not mu1 is not equal to mu2 or anything like that. It's just that at least one differs. Mu1 might be equal to mu2, just not equal to mu3. You don't know which one it is. So you can't say this part here. All you can say is at least one differs. That's it. Those words exactly, verbatim. And then find alpha. Alpha is 0.05. Done. Compute the p-value. Stat test ANOVA of L1, L2, L3, and you guys got a p-value of 0.0545. So then step 4, you're going to make the decision. So I'm going to compare p-value to alpha. P-value is greater than alpha because 0.0545. So here, you guys listen up. Give me 3 sig figs. Find your first non-zero. 5 is our first non-zero, so 5, that's 1, 2, 3. That's it. It stops right there. That's how many decimal places you have. 3 sig figs. Find your first non-zero and then start counting. 1, 2, 3, done. So 0.0545. So then I'm going to maybe for alpha, what you might want to do is have them have equal number of decimal places. So since this one has 4, add extra zeros to your alpha to make it be the same. Don't take away decimals, but you can add decimals. Add them to alpha. So you can see it's easier. 545 is greater than 500. My p-value is bigger, so I'm going to do not reject the null hypothesis. There's not enough evidence to reject the claim that the means are the same. So that's what you guys should have. Good. Any questions before I send you off? All right, so again, we're back to our notes. Go back to your notes, and you have your 11.3 notes, which is at the very back of the packet, or it might be some stand on the very next page. We already did the first one last class. One below that, lab problem 1, Pennsylvania Turnpike. Let me go ahead and move this. Greensburg bypass. It's this problem here. Do this problem now. I'm going to give you guys just 5 minutes to do it. Go ahead and work it out.
Miss Young?
Yes.
For the S value, is that the value that we see when we calculate ANOVA? Is that weird F symbol? Is that
yeah, that is. The F that you see when you do ANOVA, the F value is that value, yeah.
Okay.
And I'm not going to make you guys use it just because that'd be yet another table, and I don't want to bring in yet another table because you guys have already got 3 different tables working, and it just gets confusing. Okay, good. Okay. So let's go ahead and go over this lab problem, if I can get this to go. So can we conclude there's a significant difference? So it's saying that so this is saying concluded that there is a difference, right? So that means that they're claiming that their claim is H1, at least one mean differs. Remember on the exam, on the final, I'm only going to give you H0. It's always going to be H0, that's the claim. But here they're saying they're asking if there's a difference. So they're saying that H1 is the claim, which you'll need to know for your homework. So again, H0 is mu1 equals mu2 equals mu3. H1 is at least one mean differs. And then alpha is 0.05. Just write it down. That's it. Compute the p-value. Stat test ANOVA of L1, L2, L3. And you got a p-value of 0.0212. Again, 3 sig figs. So find your first non-zero and start writing down from there. So here, I'm going to compare. I'm going to give this a couple more decimal places so they both have 4 decimal places, and you can see a lot easier that 212 is a lot less than 500, so this is smaller. One of my students brought up this thing she learned from her tutor, who I think might have gotten from the book. I'm not really sure, but the whole idea that this is a clever sort of thing to remember. If p-value is low, H0 must go. If p-value is high, H0 will fly. In other words, it's good. It flies. It's good, right? So it's kind of a neat little thing that they came up with. And then step 5, summarize the results. So you can say that the pretty one would be there's enough evidence to support the claim that there's a difference among the means. That would be the one that your book would want. For the exam, you can just use the generic sort of enough evidence to reject the claim that means are the same. That would be okay. And I think I would even be okay with you saying enough evidence to say the means differ. That would be okay too. I'm not going to be super picky about the claim part as long as you get it right. Does that make any sense? So you can't say enough evidence to say the means are the same because we're not saying the means are the same. We rejected H naught, so the means have to be different. Okay, so here again is a summary of that if you want to see it all on one page. And you guys go ahead and do lab problem 2. So I'm going to flash up lab problem 2 real quick so you know which one it is. Do this one. If you don't have it, take a picture of it now and then go in your groups and do it. And I'm going to pop it back to the summary in about 10 seconds. And then I'll open up your room so you can go in there. And I'll give you guys 5 minutes to do this one. 1, 2, 3, 4, 5. So hopefully you've taken a picture by now. There's the results from last time. Here's lab problem 2. So we have our H naught, which is mu1 equals mu2 equals mu3, and H1 is at least one mean differs. And that was our claim in this case, I guess, because they're saying that conclude a difference. All right, so in this case, H1 was my claim. But again, on the exam, I'm going to make H naught your claim, so don't worry about that. Alpha is 0.05. My p-value, so you put it in, you got a p-value of 0.00167. Someone in my last class said, well, or my previous class said, how come you have 5 decimals this time? You only had 4 last time. It's because it's 3 sig figs. Right, you go to the first non-zero number and you start counting there. So first, second, third, 3 sig figs. 1, 2, 3. All right, so then we're going to reject the null hypothesis because when we compare the p-values to alpha, the p-value is less than alpha. Right, I put out 5 decimals here, 5 decimals there. Obviously, 167 is way less than 5,000. So like I said, it's a lot easier if you compare the same number of decimals, which means that we do have enough evidence to conclude that at least one mean differs. Okay, you could have said enough evidence to reject the claim that the means are the same, or you could have said enough evidence to support the claim that one mean differs. Those are all good. Question, go ahead.
On the exam, do you want us to write for step 4, the p-value is less than?
Yeah. Yes, I do need, that's a great question, thank you. I do need both of these because you don't have a picture. So instead of the picture, you have this instead. That is your equivalent of your picture. Yeah. And at least give me the numbers because I can probably figure out what alpha is, but I prefer to have both. Any other questions about this before we move on? Okay, so now we're going to get to the hardest part about this, which is figuring out what kind of problem is which. And people totally screw this up all the time. We talked about how exam 3, some people miss a lot of problems on exam 3 because they were not paying attention, or maybe they didn't attend the class that time, or I don't know what was going on, but they were doing hypothesis tests when they should have been doing confidence intervals. They were doing means when they should have been doing proportions, and they're doing proportions when they should have done means. So it's just all sorts of craziness in there. Or they start off as a mean and they switch it to a proportion. I don't know what's up with that. So there's all kinds of insane stuff going on. So it's really important for us to be able to figure out what kinds of problems these are. So I'm just going to kind of talk through some of the basics of these. So one thing is, if there are 2 variables right? So two variables, there's two possibilities when there's two variables. If there's two variables, maybe we'll type it out here. Either have two variables, or you have one variable. And by variable, I mean things that, actual questions, like casino size, or height, or color, not the answers, but the questions. Now, it's either going to be a category, or it's going to be a number. I should just type this, shouldn't I? Let me just type this. I think my life will be easier if I just type this. It's either going to be a number, or it's going to be a category. Same thing is true over here. It's either going to be a number, or I'll do it. Do you guys want to do it reverse? I'm going to do it reverse, category, or it's going to be a number. Okay, so whenever it's a category, you're going to have things like it's going to be a chi-squared. So these are both chi-squareds. If it's two variables, it would be a chi-squared matrix. So yeah, totally need to write that. Matrix. If it's just one, then it's just a list. Now, if it's a number, one variable is a number, then we're looking at ANOVA. And I guess I should go ahead and give you, if it's back there, then it would be two variables, then we're looking at linear regression. Okay. So those are kind of the possibilities you've got. So, so you're going to have, and here you can have means. Oh, it's okay. So in this case, it would be number, it's going to be ANOVA. So it's going to be 11.3. And then this over here, this is going to be our PPMC table, for example. Oh, maybe I'll talk about that, right? So kind of PPMC, linear regression, and we're going to be, like R is going to be involved in that one, right? So over here, this is going to be means. We're going to be looking at p-values. This is the one where you compare the p-values. All right, and then we'll kind of look down a little bit further, and we'll drop down. We'll do different colors for each one of these. These both will have some similar things. This one will be totally different. So linear regression, that's when you're kind of doing stuff. When you're gonna have words, numbers. Sorry, I've kind of gotten far afield here. So linear regression, you're gonna have pairs of data. That's kind of your hint for that one. For these guys, obviously, a matrix will be a matrix. Yeah, Yep, I'm just going to go with this. All right, so then this one, you're going to have words like frequency, or you're going to have words like proportion, because you're going to have categories, right? Kind of goes back to that categories thing. And then over here, ANOVA, these are totally going to be means. And you're going to have 3 or more lists. Okay, so that's kind of how I've sort of decided to break it down. And again, this thing comes from these categories you've got here. These are categories, right? Categories. So that's kind of how you tell them apart. So once you have categories, then all of a sudden your data is not numbers. You're talking about tally marks, frequencies, and proportions. So anytime I'm talking about frequencies and proportions, those are categories, chi-squared. So they're going to be a matrix or a list. If it's 2 variables, it's a matrix. If it's 1 variable, it's a list. If your data is numbers, 2 variables and your data is numbers, then you're almost looking at linear regression and pairs of data. In theory, it could be chapter 9 as well, right? But in terms of chapters 10 and 11, it's going to be this. You got pairs of data. You're looking for pairs of data, and you're going to be using the PPMC table and comparing R using linear regression. If there's only 1 variable, then this is going to be ANOVA. You're comparing means, and we're going to be looking at p-values. So you're going to have 3 more lists. So let's kind of look at some of the things we're looking at here. So it has 2 variables. That's chapter 10. If they're looking at a relationship between them. This is correlation, R. This is when you have that regression line, right? And you're going to use degrees of freedom n-2. These are kind of the things that you might want to put on that list also. It's going to look like this, where you have 2 different kind of variables up here, and then you have a list straight down. There's nothing along here. You only have something along the top, nothing along the side. Or you might have something along the side, but nothing along the top. It's either one or the other, but not both. This one here, chapter 11, your chi-squared list, you're going to have categories, observed and expected. Right? If it's the list, you're going to have just 1 layer of lists up top, and then on the side you're going to have your observed and your expecteds. And you'll be given the observed, you have to compute the expecteds. All right, so if you think back to your variable is your answers to your variable are categories. I know your question might be type of car. And what we have for type of car, we had or it might be, we need to have 2 different variables with it. So it might be mammal, type of the animal, and whether it's endangered or threatened. So it might be like bird that's endangered, or reptile that's threatened, something like that. So you're going to have, oh, my bad, this is the first one, the list. So it's going to be, this one would just be like flavors of ice cream you like, right? So then just a list of different ice creams, and then your observes, and then your answer is going to be things like strawberry, chocolate, vanilla, mint chip, right? You're not going to say 3 or 7 or 14. What's your favorite ice cream? 14, right? Your answers are going to be categories. For your matrix, again, your answers are going to be categories, right? It's a chocolate lab, and he's a male. It's a yellow lab, and she's a female. You're going to have 2 different variables, but your answers again are going to be categories, and it's going to look like a matrix. You're going to have categories up top and categories along the side. Chapter 11.3, you have multiple lists, which means that you only have categories across the top or the side, but not both. one or the other, and then you have a list of numbers. And then also you can have the word means in there as well. So you might want to take a picture of this just to kind of help you organize your thoughts on some different things you want to kind of, I try to maybe pack too much stuff in here, I don't know, but I want to give you guys kind of all the information that I could kind of come up with everything. Okay, so we're going to move on. So I want you guys to take a look at this and decide which of these pictures is which. One is chapter 10, linear regression, one is a chi-squared list, one is a chi-squared matrix, and one is ANOVA. So take a look through them and decide which is which. Take 30 seconds on your own, go. Okay, so this one over here on the far right, which one is this one? Private chat me. What's this one on the far right? I heard from 2 people. Only 2 people know? Oh, 3, there it goes, much more. Good, it seems like you guys are on board. So here I have categories up top, kind of, and down here, but actually these aren't even categories. So I have things up top and I have titles up top, but no titles along the side. You guys see that? I only have titles in one spot. So when I look at that, oops, no. Okay, I only have titles in one spot. So I know right away it cannot be a matrix because I only have titles in one place. It also can't be chi-squared at all because I either have to have categories in both spots, categories across the side and the top, or I have to have observed expecteds in one and categories across the other one. I don't have that one. So then I'm only down to either ANOVA, which is 3 or more lists. This is not 3 or more lists, this is only 2 lists. So this has to be, just by looking at it visually, this has to be chapter 10. Right, I have my X and I have my Y. And the thing about it too is these are not even categories. These are different things completely. So age and net wealth, those are not different categories of the same variable. Those are completely 2 different variables. So this is chapter 10. How about this bottom one? We'll start with the bottom one down here. Do that one next. What's this one down here? So it's definitely chapter 11, but there's 3 different possibilities. Heard from 3 people. No one else knows? 4 people have given an answer. 5, 6, 7. Okay, so this one, the bottom one down here, the very bottom one. All right, so one might say, okay, well, I got labels here and I have labels there, so maybe it's a matrix. Except the thing about it is, it's definitely, I have labels and labels, so it's definitely chi-squared. But my labels are observed and expected. They're not actual real labels. They're just observed and my expected. So this would be a chi-squared list. Do you guys see what I'm saying? Because really it's just, these are my only observed. Okay, so let's go ahead and take a look at the top one up here. The top one, so it's this one right here. Can you see my mouse? People don't see my mouse? This one here. This one here. I've heard from 3 people. Okay, so some people who are a little bit confused. All right, so is this a matrix? I don't have anything here. A matrix has to have things on the side and the top. I have categories across the top. I don't have categories along the side. It can't be a matrix. It has to have two different variables, right? It has to have things along the side and the top in order to be a matrix. This is not a matrix because it does not have anything along the side, only along the top. Instead, what it has three lists. L1, L2, L3, three or more lists. This is ANOVA. That's the 11.3. Again, this last one here, the gender, football, baseball, hockey, do that one. All right, everybody seems to be in on this one. That's good. So this one, again, is we have categories here, and we have categories there. We have, and male and female are not observed and expected. Male and female are two different things. So we have categories here and categories there. So this one is my chi-squared matrix. All right, this one is 11.2. Good? I think I have it here as well. This is a little bit better written. So it's super important you guys be able to, so one, there's two ways. You can find it visually, right? Or you can find it from those other things we talked about in terms of variables, number of variables, whether your data is numbers or categories, and whether you're talking about proportions, you know, things like that, frequencies. Okay, so let's go ahead and hop in to these problems here. Oops. So I want to take 15 seconds and try to figure out what kind of problem this is. You can do it visually, you can do it from the words, you can do it from any sorts of different things. Many, many different options. I've heard from two people. Final on this coming up soon, guys. You need to be able to do the correct problems with the correct ones. This is important. I've heard from 4 people so far. All right, so we definitely have categories across the top. Everybody on board with that one? So the question is, do we have categories along the side or not? We have something along the side, so it's definitely a chi-square because I have something along the top and something along the sides. Now, along the sides, is that observed expected along the sides, or is that different categories? Those are categories. Yep, so this is a matrix. The other thing, the other way you know, is that you see the word, see this percentage here? Percentages are always going to be, always going to be chi-squareds. So that's another hint that's a chi-squared. And then see the word proportions here? Ooh, proportions. And the test for homogeneity proportions, well, that's kind of a hint. It probably won't be that obvious. But you're talking about proportions. So let's see if this actually went along with that. That would be useful. Yeah, sort of. Okay, great. This might be it. Yeah, so proportions. Good. Now the next one is going to be this guy here. I want to take a look at that one. Let me know what you think. I have 1 answer, 2 answers, 3, 4, 5, 6. You can't answer the same thing twice. Only 1 answer per person. All right. So I do not have categories up top and on the sides. So this cannot be any of the chi-squareds. You guys understand what I'm saying? Chi-squareds should have you know, categories along one and observed expected along the other ones, or categories and categories. So then, since I only have two, I'm going to be looking and seeing if it's linear, and maybe it is. So then we see, oh, linear correlation. That's another thing that tells me it, right? And then we see, are these two different variables, opening bid and winning bid? Yeah, they're actually two different ones. This is my x and this is my y. And these are all pairs. So this is a linear correlation. Oops. Well, that kind of got screwed up, didn't it? All right, try this one. Quickly, we only have a couple minutes, guys. Get on it. So do I have categories across the, where do I have categories? I have categories here. Do I have categories on the side also? So if I have categories on top and the side, then it's a matrix. That makes it a matrix. It's a contingency table, right? Lists are only going to have it one or the other. So here, and the other thing too is, let's see if we read it, blah, 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 independent, that's okay. So this one is also a chi-squared matrix. Don't look. We have three more. Let's try to get them knocked out quickly. One answer, two answers, three. I don't even have a table. I need to make my own table of this one. So if I were going to make a table, what would I do? Frequencies go from 0 to 9. And then we have our, and then these are the frequencies. So what are these guys here? Those guys are labels. These are, see the word frequencies here? Once you see the word frequencies also, that's another hint that this is a chi-squared. Frequencies are always going to be chi-squared. So the question is this a list or a matrix? Obviously a matrix, I have to give you a matrix. So this has to be a list. So this is my list right here. These are my observeds. And, oops, this is, what I did was actually better than this. This is kind of a mess. And then I have to figure out the expecteds from there. Okay, just two more. We need to do two more quickly. What's this one? Four people. Only four people know? Good. All right, there we go. So this is, there's nothing up top. There's only something along the side, so it's got to be either, it can't be chi-squared at all. So I have three or more. These are lists. L1, L2, L3, and also the word mean. See that word mean there? That's another hint. We're comparing means. So this is ANOVA. All right, last one. This one here. What is this one? This one's a little tricky. You got to read it. Nice. 3 people. 4 people have it. 5 people have it. Okay. A couple people are confused. Okay. So I have okay. So figure out what this is. It looks like it could be 3 lists, right? That seems totally likely. There's 3 lists, but then you got to read it and kind of see what it is. We're saying that if it's 3 lists, we should talk about means here somewhere instead of talking about proportions, right? So then that means when you're talking proportions, it has to be chi-squared. So let me look at this. We're talking about playing games for the World Series. So this is the number of games played. So this is actually, these are categories. These are not actual values. These are categories. So then I have to look here and say, okay, are these categories also? So it's a chi-squared matrix. But what actual really means what? Actual means observed, and expected means expected. So this is actually a chi-squared list. So this one's, also you talk about expecteds here. So if you look at it, it's actually a chi-squared list. All right, so that's enough for today. We'll go through some more. I know it's tricky. That one's tricky. Mine won't be as tricky as this one. My categories won't be numbers too either. I promise you that. But just be aware. We'll see you guys on Thursday, and we'll go over a few more of these because again, it's really important that you be able to tell these apart. If you don't, you're going to do the wrong thing, and you're going to miss a chunk of points. Right? I've only got 4 of these problems on there, and 35% of your exam. So each one of these is like 8% of your final, which is huge. So we'll go over some more. Have a great couple days. It was really good seeing you guys, and all right, take care. Have a good one. Thank you. Yeah, and stick around. If you have a question on the homework, you can go ahead and ask me. Let me try to save this. Let me stop this.